This is Edmontosaurus. He is about 12 meters long and weighs around 4 tons, roughly a young African elephant with 9 meters of tail and neck added on. He walks on 4 legs but can rise onto his back too when he wants to reach higher or run. He has no horns, no armor, no claws. There is nothing anywhere on his body built to hurt another animal, and there are thousands of him. He is standing near the edge of a herd so large that you would have to climb a hill to find the end of it. And the sound it makes at this hour is not a roar, it is the sound of several thousand animals chewing. His mouth is the strongest. Behind that flat, wide, duck-like beak sits somewhere over 1,000 teeth, not loose in the jaw like a crocodile's, but packed into dense columns, cemented together into a solid grinding surface. As he closes his mouth, the bones of his upper jaw bow outward. The surfaces slide across each other. He is milling his food, and the teeth wear down and are replaced from below, continuously for his entire life. Nothing alive today has a mouth like this. He is eating conifer needles and ferns in the half-light, on flat ground, beside a slow river. And the ground he is standing on was, not very long before this morning, the floor of an ocean. The date is roughly 68 million years ago. The planet he lives on is not the one you live on. It has no ice at either pole, none at all. Its sea level is so high that the ocean has flooded straight across the middle of continents. Its air holds several times the carbon dioxide yours does, and that single fact reaches into everything. How hot the poles are, how fast plants grow, how big an animal can get, and eventually, how the whole thing ends. This is the story of that planet. Not the animals in it, the machine underneath them. And the same thing that built the largest creatures ever to walk on land is the thing that killed them. We start at the bottom of the world. Step out onto this world and the first thing that would strike you is not a dinosaur. It is what is missing. There is no meadow. Look in any direction and you will not find one. No lawn, no prairie, no pasture, no hay. Grasses do exist by now, just barely. We have found their microscopic silica particles preserved in fossilized dinosaur dung. But grass is a rare curiosity growing in patches, not a carpet. The great grasslands, savanna, steppe, prairie, are still tens of millions of years away, and every animal in this story will be dead long before the first one appears. What covers the ground instead is ferns, low, dense, endless. Above them, conifers of families that mostly still exist, Araucarias, podocarps, redwoods, cypresses, and tree ferns and cycads with their stiff crowns. And threaded all through it, something new, flowers. Flowering plants arrived early in this period and spread faster than almost anything in the history of life, because a flower is essentially a contract offered to an animal. Carry my pollen, and I will feed you. Magnolias, laurels, sycamores, water lilies. For roughly 100 million years before this, the forests of Earth had been green and brown and nothing else. The world Edmontosaurus walks through has color in it, and it is recent. Now look at the coastline. Or rather, try to find it. Sea levels in the Late Cretaceous stood as much as 200 meters higher than today's. Not 2 meters, 200. Water that high does not simply move beaches inland. It drowns continents from the middle. For most of this period, North America is not one landmass. It is two, split lengthwise by a warm, shallow sea running from the Gulf of Mexico all the way to the Arctic Ocean. You could have sailed from what is now Texas to what is now the Northwest Territories without ever seeing open ocean on either side. That sea is full of things that are not fish. Long-necked plesiosaurs, mosasaurs, marine lizards, some of them over 12 meters, with jaws hinged to swallow whole. Ammonites the size of tractor tires. Above it, pterosaurs with wingspans wider than a small aircraft. Europe barely exists as a place. It is an archipelago, a scatter of tropical islands in a shallow sea, and we will come back to what that did to the animals stranded on them. And at the poles, there is no ice. That is the part that is hard to hold in your head, so hold it slowly. Not less ice, not thinner ice. For much of the Cretaceous, the best evidence we have says there were no permanent ice sheets on this planet at all, at either end of it. The Arctic Ocean is a temperate sea. Antarctica is a continent covered in forest, which is not a metaphor. We have the roots. In 2017, a research vessel working off West Antarctica drilled into the seabed of the Amundsen Sea embayment in the shadow of the Pine Island and Thwaites glaciers. It is one of the coldest, most hostile stretches of ocean on Earth. The drill went down through the sediment and came back up with something nobody had planned for. Inside a layer of mudstone was a network of fossilized roots, 3 meters across, still in position, not washed in from somewhere else, not scattered debris, but a root system sitting exactly where it grew. Around it, pollen, spores, and the chemical traces of soil. The layer dates to between 92 and 83 million years ago. At that time, that patch of ground sat at about 82 degrees south. For scale, the South Pole itself is 90 degrees south. This is 900 kilometers from the pole, deep inside the Antarctic Circle, in a place that today is under kilometers of ice. And it was a temperate rainforest. The reconstruction that came out of that core describes a mean annual air temperature of around 12 degrees Celsius, roughly what northern Italy or Washington State gets now. Summer temperatures near 19, rainfall comparable to modern Wales, rivers and swamps. Conifers, tree ferns, and flowering plants growing in soil that had been forming there for a long time. Now here is the problem, and it is a good one. Move a forest to 82 degrees south, and you have not changed its temperature problem. You have changed its light problem. At that latitude, the sun does not rise for roughly 4 months of the year. Not dim, not low, gone. A third of every year in complete darkness, and no amount of carbon dioxide in the atmosphere can put light back into a sky the planet has tilted away from the sun. Plants cannot photosynthesize in the dark. So how does a rainforest survive a third of its life without any light at all? The answer is that it stops. These forests were built out of trees that shut down. deciduous conifers and broad-leaved plants that dropped their foliage and went dormant, running on stored reserves through the dark months, the way a maple in Vermont runs on nothing through February. We can see it in the wood itself. Fossil trees from high Cretaceous latitudes show growth rings, and the rings are wide, very wide. Wider than most temperate trees today, because the other half of the deal is summer. If the sun does not rise for 4 months, it also does not set for 4 months. Those trees got a continuous 24-hour growing season at temperatures that never froze, in an atmosphere loaded with carbon dioxide. They spent a third of the year asleep and the rest of it growing at a rate no modern polar plant can match. That is the first thing the greenhouse built. A forest where a forest should be impossible, running on a rhythm of feast and shutdown that no ecosystem on Earth uses today. And there were animals in it. Not many that we have found. Antarctic rock is under 2 kilometers of ice, and every fossil from that continent comes from a handful of exposed edges. But we have an armored dinosaur, Antarctopelta, from the Antarctic Peninsula. We have a small plant eater, Morosaurus. We have a predator, Imperobator, with feet built for something other than the killing claw its relatives carried. They lived through the dark months too. Nobody knows exactly how, whether they migrated, whether they slowed down, whether they simply ate less. That is a genuinely open question, and it is one of the reasons Antarctic paleontology is worth the cost of getting there. Hold on to the mechanism, though, because we are about to watch it do something much larger. Warm poles mean the temperature difference between the equator and the poles collapses. A smaller difference means weaker winds, weaker ocean circulation, and a wetter, more uniform world. Combine that with carbon dioxide levels several times modern values, and you get a planet where plants grow almost everywhere, almost constantly, which sounds like paradise for a herbivore. It was not. There is a thing that high carbon dioxide does to a leaf that took a long time for anyone to notice. Plants grown in carbon-rich air grow faster and bigger. That part is obvious. But the extra growth is mostly carbon, sugars, cellulose, structure. The nitrogen and the minerals do not scale up with it, because those come from the soil, not the sky. So the leaf gets larger while the nutrition inside it gets thinner. More food, less feeding. That is measurable in modern experiments, and it is one of the working explanations for what we see in the Mesozoic fossil record, though it is not settled and you should hold it loosely. But the plants themselves argue for it. Conifer needles, cycad fronds, tough ferns, these are terrible food, fibrous, waxy, low in protein, expensive to break down. Imagine being handed an unlimited supply of something that barely feeds you. There are 2 ways an animal can solve that. It can evolve an extraordinary mouth and grind the material into paste before swallowing, which is exactly what Edmontosaurus and the other duckbills did with those 1,000-tooth mills. Or it can go the other way entirely, swallow enormous quantities without chewing at all, and hold the material inside the body long enough for microbes to do the work. That second solution has a size requirement. The bigger the animal, the longer food stays in the gut, and the more of a bad meal can be extracted from it. Push that logic hard enough, and you do not get a large animal. You get the largest animals that have ever walked on this planet. Sauropods, long neck, small head, enormous barrel of a body, 4 pillar legs, long tail. The body plan is essentially a walking fermentation vat with a feeding arm on the front, and it worked for over 130 million years. In southern Patagonia, in rocks about 77 million years old, a team excavated one of the most complete large sauropods ever found and named it Dreadnoughtus. About 26 meters long. The skeleton is roughly 70% complete, which for an animal this size is extraordinary. Most giant sauropods are known from a few vertebrae and a lot of hope. The first published mass estimate, calculated from the circumference of the upper arm and thigh bones, came out at 59 tons. That number went around the world. It has since been argued down substantially. Several later analyses, using body volume modeling rather than limb scaling, put it closer to 30 or 40. And the bone tissue says the animal was still growing when it died. It was not an adult. I am telling you the argument rather than a single number on purpose, because the argument is the interesting part. We are trying to weigh an animal from the thickness of its arms, and we do not fully agree on how. What we do agree on is how it stayed off the ground. Cut open a sauropod vertebra and it is not solid bone. It is a honeycomb, hollow chambers threaded right through the skeleton, in the neck, the back, sometimes into the hips. Those cavities held air sacs, part of a breathing system in which air moves in one continuous direction through the lungs rather than in and out like a bellows. Birds still have it. It is why a goose can fly over the Himalayas at an altitude that would leave you unconscious on the floor. For a sauropod, that system did 2 jobs at once. It made a 15-meter neck physically possible, a solid bone column that long would collapse under its own weight, but a scaffold of struts and air will hold. And it helped shed heat, which matters enormously when you are a 40-ton animal in a greenhouse world with no way to sweat. So the chain runs like this. Carbon in the air makes plants abundant and poor. Poor food selects for enormous guts. Enormous guts need a body that can carry them without breaking or overheating. And that body already existed, inherited from small 2-legged ancestors who happened to breathe like birds. The planet did not decide to make giants. It just set the conditions, and the giants were the only shape that fit. And an animal that large drags everything else upward with it. The predators hunting these herds are 8, 9, 12 meters long. The herbivores that cannot outgrow the problem grow armor instead. Plates, spikes, clubs, and the great bony frills of the horned dinosaurs. Every one of those structures is a response to something else in the same forest. Now let's put a face on it. Because until recently, we did not know what any of this looked like. For most of the 20th century, dinosaur color was a matter of taste. Museum artists painted them gray or green because elephants and lizards are gray and green, and there was no evidence to argue with. Then, in northeastern China, quarries in the Jehol beds started producing fossils preserved so finely that you can see the outline of soft tissue around the skeleton. Around some of these animals is a dark halo, filaments running along the neck, back, and tail. The first fight was over what those filaments were. One camp said feathers. Another said decayed collagen fibers from the skin. It was settled by looking closer. Under an electron microscope, the filaments contain structures a fraction of the width of a human hair, oval and rod-shaped bodies densely packed. They are melanosomes, the organelles that carry pigment. They are found in feathers, hair, and skin. They are not found in collagen, and here is the part that changes what you can put on screen. In living birds, the shape of a melanosome correlates with the color it produces. Rod-shaped ones tend toward blacks and grays. Rounder, oval ones tend toward reddish browns. Line up the fossil melanosomes against a reference library from modern birds, and you can start reading color off a rock. Sinosauropteryx, a small, fast predator about a meter long. Most of its tail comes out ginger brown, with alternating light and dark bands running down the tail. Later work on the same species mapped the pattern across the whole body. Dark on top, pale underneath, which is countershading, the same camouflage scheme a deer uses. And a dark stripe across the eyes, like a raccoon's mask. Countershading is informative in a way that is easy to skip past. The exact gradient tells you about light. Animals living in open, brightly lit habitat have a sharp transition. Animals under forest canopy have a soft one. Sinosauropteryx has the sharp version. This animal lived in the open, not in the trees. We reconstructed the habitat from the paint job. The same work has been done on others. Confuciusornis, an early beaked bird, comes out patchy, dark and light in blocks rather than bands. Sinornithosaurus, a small feathered raptor, shows a mix of pigment types across the body. Be careful with how much you take from this. Melanosome analysis reads melanin-based colors well: blacks, browns, grays, russets. It does not read the brilliant blues and greens of a modern kingfisher, because those are structural colors produced by the physical architecture of the feather, not by pigment, and that architecture usually does not survive. So the palette we can recover is real, and it is also incomplete. The Cretaceous may well have been far more colorful than we can currently prove, but it kills the gray lizard for good. These were feathered animals with patterns, countershading, and probably display. And display only exists if somebody is looking. Feathers, meanwhile, are not primarily about flight. They show up in the fossil record on animals that could not possibly have flown, in forms ranging from simple hollow filaments to complex branching structures. They insulate, which matters more than you would think on a warm planet with 4-month polar nights. They signal. And on one branch, in a small number of species, they eventually catch air. We will come back to that branch. It is the only one that gets out of this alive. While all of this is happening, The ground itself is coming apart. At the start of the age of dinosaurs, every continent on Earth was fused into one landmass. An animal could walk from what is now Norway to what is now Antarctica without crossing water. By the Late Cretaceous, that is finished. The Atlantic is open. South America and Africa have separated, with a young ocean widening between them. India has broken loose entirely and is moving north across the Tethys Sea as an island continent, at a speed that is fast by geological standards, and will eventually put it into the underside of Asia hard enough to raise the Himalayas. Add the flooded interiors on top of that, and the map stops being continents at all. It becomes a scatter. For evolution, this is an accelerant. Separate two populations and they stop exchanging genes. Each one then drifts, adapts, and specializes against its own local conditions until they are no longer the same animal. Do that to an entire planet at once, and you do not get one Cretaceous fauna. You get a dozen parallel experiments running simultaneously, each one solving the same problems in a different way. In North America, isolated behind the Great Inland Sea, the experiment produces horned dinosaurs and duckbills in enormous numbers and a single family of huge predators with reduced arms and skulls built to crush bone. In South America, cut off to the south, the same ecological roles are filled by completely different animals. The giant plant eaters are titanosaurs. The sauropods, which had declined elsewhere, stayed dominant here and produced the largest of them all. The apex predators are abelisaurs, deep-skulled, blunt-faced hunters with arms even more reduced than a tyrannosaur's, essentially useless stubs. Two continents, same jobs, entirely different applicants. And then there is Europe, which was not a continent at all. In what is now Romania, rocks from the very end of the Cretaceous preserve a place called Hotseg Island, a landmass of maybe 80,000 square kilometers, isolated in a shallow sea. And the animals on it are wrong. Magyarosaurus is a titanosaur, a member of the family that produced 30-meter giants on the mainland. On Hotseg, it is 6 meters long. Full-grown, the bone tissue confirms these are adults, not juveniles. The duckbills there are similarly reduced. This is island dwarfism, the same process that produced dwarf elephants on Mediterranean islands millions of years later. Limited space, limited food, no room for a large body. But the island did not shrink everything. Above these miniature giants stood Hatzegopteryx, a pterosaur with a wingspan estimated around 10 to 12 meters and a skull nearly 3 meters long, which spent much of its time walking on all fours on the ground, hunting like a stork the size of a giraffe. With no large predatory dinosaurs on the island, something else took the job. That is what a fragmented planet does. Not one story, dozens, each one written by whatever happened to be trapped where, by 68 million years ago. The family, that started as a minor group of small two-legged animals, is on every continent on Earth, including Antarctica. It ranges from creatures the size of a crow to creatures weighing more than a loaded truck. It has been the dominant land vertebrate group for over 130 million years. It has about 2 million years left. The end of this world is usually told as a single afternoon. It is more accurate, and considerably worse, to tell it as a long illness followed by a fatal accident. Start with the illness. In what is now Western India, beginning a few 100,000 years before the end of the Cretaceous, the crust opened. Not a volcano, a series of enormous fissures pouring flood basalt across the landscape in successive sheets. The Deccan Traps eventually covered an area of hundreds of thousands of square kilometers, in layers stacked over 2 kilometers deep in places. You can still drive through them. They form the flat-stepped hills across much of Maharashtra. Eruptions like that do not primarily kill by lava. They kill through the atmosphere. They release carbon dioxide, which warms the planet, and sulfur dioxide, which cools it sharply in short bursts and falls out as acid. The record around this interval shows exactly that signature: temperature swinging, oceans acidifying, and a global carbon system under sustained strain for a very long time before the end. So the biosphere going into the final act is not a healthy one. It is a highly specialized, heavily interlocked system. Remember, these are the most specialized dinosaur communities that ever existed, each one fine-tuned to its own isolated landmass, already absorbing repeated shocks. Then, on an ordinary day about 66 million years ago, something arrives. An asteroid roughly 10 to 15 kilometers across strikes the shallow water at the edge of what is now the Yucatan Peninsula at around 20 kilometers per second. It excavates a crater more than 180 kilometers wide and punches through the crust, deep enough to leave a permanent scar in the gravity field of the planet, which is how it was found in the first place, not by a geologist looking for a crater, but by an oil company survey noticing that the rock underneath was the wrong shape. We know the date with a precision that is genuinely startling. Volcanic ash layers just above and below the boundary contain crystals of sanidine, which can be dated by the decay of potassium into argon. Run at high precision, those layers put the impact and the extinction within about 32,000 years of each other, which, at this depth of time, is the same instant. Whatever killed the dinosaurs and the asteroid are not two separate events, separated by a gap we can measure. Now follow the damage outward, because the impact itself is the smallest part of it. Molten rock is thrown up out of the atmosphere and comes back down across the entire planet as glass droplets, heating the sky as they fall. That layer of tiny spheres is found worldwide, and it is one of the reasons we can pin the event so tightly. Then the dust, billions of tons of pulverized rock, thrown high enough to circle the globe and stay there. And then the part that mattered most. The rock at the impact site was not ordinary crust. It was thick with sulfur-rich evaporite, gypsum and anhydrite, laid down by an evaporating sea. Vaporize that, and you inject sulfate aerosols into the stratosphere, which is the most efficient sunlight-blocking substance the planet has. The models disagree about severity and duration, but they agree about direction. The sky darkened and the surface got cold, fast. Photosynthesis stops. That is the actual mechanism. Not fire, not the shockwave, not the tsunami. The carbon engine that had run this world for 130 million years, sunlight into plants, into enormous herbivores, into enormous predators, was switched off at the source in a matter of weeks. And the animals with the greatest caloric demand on Earth were standing at the top of it. A 4-ton Edmontosaurus needs an immense and continuous supply of plant matter. So does every one of the several thousand animals standing beside him. When the vegetation fails, a herd that size does not adapt or migrate to somewhere better, because there is no somewhere better. There is only a smaller and smaller amount of food, and far too many mouths. The herds go first. The predators that lived on the herds follow them down within the same short window. In the ocean, the collapse runs top-down as the plankton fail, and it takes the mosasaurs and the plesiosaurs and the ammonites with it. Roughly 3 out of 4 species on Earth do not survive this. There is still real argument about how to divide the blame, whether Deccan volcanism had already crippled the biosphere and the impact merely finished a job in progress, or whether the impact was so overwhelming that the volcanism barely mattered. Both camps hold serious evidence. What is not in dispute is the shape of the outcome. An intensely specialized world, built by and for a stable greenhouse, met a shock that removed its foundation and had nothing left to fall back on. Go to the right rock face today, in Colorado, in Denmark, in New Zealand, and you can put your finger on the moment. There is a thin band of clay, sometimes only a centimeter or 2 thick, enriched with iridium, a metal that is rare in Earth's crust and common in asteroids. Below that line, a complex ecosystem. Above it, almost nothing. And then, immediately above, ferns. Overwhelmingly ferns. Palynologists call it the fern spike, and it is what a devastated landscape looks like in pollen. The forests are gone, and the first thing to move into open, ruined ground is the plant that spreads by spores and asks for nothing. So who is left standing in the ferns? Almost everything that survives has the same profile, and it is the opposite of every animal in this documentary so far. Small, first of all. Body size is the strongest single predictor of who made it through. If you weighed more than about 25 kilograms, on land your odds were close to 0. Sheltered, second. Animals that lived in burrows or in water were buffered from the initial thermal pulse and from the temperature swings that followed. Freshwater ecosystems came through startlingly well: crocodilians, turtles, amphibians. Their food chains ran substantially on dead organic matter washing in from the land, and detritus does not need sunlight. When the surface world starved, the river bottom kept eating. And third, able to live on seeds. A seed is a package of stored energy that sits in the soil and waits. In a world where nothing green is growing, the ground is still full of food for anything small enough to find it and patient enough to dig. Which brings us to the one branch of the dinosaur family that does not end at that clay line. Deep inside the meat-eating branch, the same lineage that produced the largest predators of the Cretaceous. A group had been getting smaller for tens of millions of years. Lighter bones, hollowed by the air sacs, better feathers, stronger shoulder muscles, beaks without teeth. By the end of the Cretaceous, some of them were small ground-living seed-eaters, unremarkable next to the giants. That is the profile that survives: small, able to hide. Able to eat seeds, they are birds, not descended from dinosaurs in the way people usually say it. They are dinosaurs, on the same branch of the same family. An unbroken line running back through the theropods to small two-legged animals that were already breathing with one-way lungs and growing feathers 160 million years earlier. There are around 11,000 species of them alive right now. One of them is probably within 100 meters of you. Here is the last thing. And it is the reason this planet is worth understanding rather than just watching. That great inland sea that split North America did not vanish without leaving anything. It filled with the shells of countless microscopic organisms, layer on layer, for tens of millions of years. That sediment is now rock, and that rock is now the ground under the wheat belt. The chalk of Kansas is the floor of an ocean that had mosasaurs in it. The white cliffs on the English coast are the same story, laid down in the same period. If there is limestone in your kitchen, or a chalk mark on a blackboard, or cement in the wall beside you, some of it came out of that world. The greenhouse left its record everywhere. In the oil and gas that formed from Cretaceous organic matter. In the shape of the Himalayas, which exist because India was already moving north while all of this was happening. In the 11,000 species of small feathered dinosaurs that survived the day the sky closed. And in the ground itself. 68 million years ago, a 4-ton animal with 1,000 teeth stood on a floodplain in the early morning, chewing conifer needles in a herd that stretched past the horizon. He was standing on the drained floor of an ocean, under an atmosphere that would eventually kill his entire family, on a planet with no ice at either end and a rainforest where the South Pole should be. That world was not a prelude to ours. It was a fully functioning version of this same planet, running different settings, and it lasted, in that configuration, for far longer than mammals have existed. It is still down there. Compressed, tilted, quarried, and built into the walls around you. If you want to keep walking through Earth's older worlds with us, subscribe. And tell me in the comments which of these places you would want to stand in for 1 hour. Next time, we go back further, to an Earth that Edmontosaurus himself would not have recognized.